Alright, so I think you're all familiar with the polar notation of coordinate systems, right? So Cartesian systems is a pretty well-known coordinate system, alright? But let's say, for example, there is a point in a 2D space that the position of which is denoted by x and y. So you have to travel starting from O towards x for an unit of x, and then we will have to travel along y direction to a distance of y to get to the point P, right? This OP line over here has length. Let's say this is R. All right, so there's another way to reach the P point over here. That specific way is to first determining the distance from the origin to the point P over here. That means the uh, length of OP line that will be denoted by R, and then you will just move around the radial line, if we call it. You will just move around it starting from a specific point. So the convention is starting the rotation from the OX position. So let's say the radial line is uh, along the X direction first, and then you rotate the radial line towards uh, the anti-clockwise direction. By an angle of phi to get to the P point, right? If the P point was over here, then you would have to move, you would have to cover a slightly more angle over here. So the value of the angle over here would be different, but the radius would not be any different. So even though the point over here, the P point over here and the P point over there are the same point, but the notation according to which coordinate system we are using, the notation is what's changing over here. So if we are using the Cartesian coordinate system, we denote the position of P by x and y, and if we are using the polar coordinate system, that is slightly different from this method over here. So we denote the coordinates by a radius and an angle it makes with the positive direction of x-axis, right, towards the anti-clockwise direction. Remember that these 2 points, the P point over here and the P point over here, are the same, and they are the exact same thing, but the way we're approaching the point is what's changing in the two coordinate systems that we're using. In this case, you will just move straight along the OX direction, then move straight along the Y direction. And in the polar coordinate system, you will just select a radial line over here that denotes the distance from origin to the target point we're trying to reach, and then the angle it makes with the positive direction of x-axis. All right, so this is the way we can approach a point differently. Now if we were to convert this thing into the 3D projection, like we did before in the case of Cartesian coordinate system, we'll just add another axis perpendicular to both x and y axis. So let's just say there's another third axis, and there's perpendicular to both x and y, and that is z, and that is uh, pointing directly outwards from the surface you are looking at right now. And this will just cause an elevation to the point P over here, right? I guess that's clear. So let's transform this concept of polar coordinate into this picture over here. Okay, so here we are again with the familiar 3 coordinates over here, x, y, z, all perpendicular to the other. We'll have to specify the P point, but this time with a cylindrical coordinate system, all right? Okay, so before we go into any further discussion, please remember that we used 3 different variables to denote the coordinates in Cartesian systems, and those were x, y, and z. And in this case, cylindrical coordinate system, the 3 variables we'll be using will be r, phi, and z. So the r and phi over here are straight from the polar coordinate system that you are familiar with, and the z is the same as the z of Cartesian system. that introduces the elevation to the polar coordinate system. Previously, we've shown you the polar coordinate with an x and y axis, that means the 2D space, right? So if you look at these pictures from the top, this xy plane is the same thing that you were looking at over here, all right? Okay, so first let's forget about the z-axis altogether. Let's say you are taking the projection of P point on the xy plane over here. That means this is this point. A projection means the, if we call it the shadow of a point, if a light was to be shed on it. For example, say a light is shed perpendicularly on this point P, would create a shadow of P point over here, right? So this is called the projection of P. Okay, so let's just recap the polar coordinate system over here. So let's say this point, to get to this point, we would have to cover this length over here. So let's name it P prime, for example. So OP prime might be called the radial line, all right? So first of all, we would have to know the distance of P prime point from the origin. And we would also have to know the angle it has to cover, starting from the positive x-axis to get to the point over here. So let's say we only have this line over here and we don't know what to do with it, then we just have a brilliant idea, then just place this point over here to origin and start moving about the other point to by an angle. So this should be creating a circle, right? If we were to take uh, line along the x-axis and then we were to rotate it all together, we would get a circle. Okay, so let's say we just know about this OP prime line that has a length of r, and then we start moving it from starting from the positive x-axis into an anti-clockwise direction. To understand what's going on over here, when I say the anti-clockwise direction, I am mapping this direction over here. All right, so we would have to move the r length line by an angle of say phi to get to this point, right? To get to this state, and then we just make an elevation to the line, like we just lift this line up by a distance of z, all right, to get over here. Sorry. So first we just figure out the distance from the origin to the projection of the point we're targeting, and then we just find out the angle it has to cover starting from the positive x-axis to get to the projection line of it, and then we just lift this line by distance equals to z to get to the point over here, right? So if we just move this point and this point all together upwards by direction z, you will just move it along this direction until you get your tip of the line over to the point that we are trying to specify, right? So there are three variables that are going to specify the point over here. The first one is the distance from the origin. Okay, this distance, this r, is a little tricky. This r is not the distance of point P from origin, right? This this is rather the distance of P from the z-axis, all right? This is perpendicular, of course. And also, you can say r to be the distance of the projection of p from origin, or the distance of p from the z-axis. Why? Because there is sort of like a DC shift over here, so there is just a separation equals to z over here, right? So in this case, to denote the point in cylindrical coordinate system, we need three variables. R, the R is the distance of P point from the z-axis. Then phi, the angle that this line makes with the positive direction of x-axis, and the z, the elevation of this line over here, or this P point over here, from the xy plane, right? So if you find it hard to follow, then just pause and rewind to get back again to have a better understanding of it. But I'm repeating this thing all over again. So first of all, we have this distance of the P point from the z-axis, right? And this distance is given by r. But first of all, let's map the polar coordinates into this picture. So we would have to just tone the elevation down to the x-axis. So we would have to just take the projection of P onto the xy plane. And this r remains the same because it just comes down. Then this radial line creates an angle equals to phi with the positive x direction over here, and then the elevation is z. So we get r, the distance between P point and the z-axis, the phi angle, that the angle this line makes with the positive direction of x-axis, and then z, the elevation of P point with the xy plane. So these are the coordinates we will be using over here. And now let's explain why this line is called the radial line. All right, so whenever you are moving about uh, anti-clockwise direction with a specified length, let's say you have 5-unit length of line along the x-axis, and let's say you just moving it about along the phi axis. All right, so you're just moving it around, moving it around until you get to the same point again. So you are getting a circle over here, right? And then if you were to move that circle upwards from the xy plane along the z direction, you would get a cylinder, right? If this is the part of your let's say this is the part of the circle you are covering, and you just would want to elevate all of the circle upwards, you would just end up over here. Let's say you just move all the circle all together upwards, you would end up getting a cylinder in the end. All right, so Cartesian coordinates were creating a rectangular parallelepiped, whereas these three coordinates are creating a cylinder as you go forward. All right, so this is called a cylindrical coordinate system because of that, and the r variable over here denotes the radius of the cylinder. All right, so that's why we're calling it the radial line. Okay, so I hope that you figured out what was really going on over here. And time now to get to the three orthogonal or perpendicular unit vectors related to these three coordinates. All right. So when we were talking about the Cartesian coordinate system, we were mentioning x, y, and z. So the unit vectors associated with them were ax, ay, and az. All right. And whenever we will be using cylindrical coordinate system, we will be discussing about ar, a phi, and AZ. All right. So let's now define these three unit vectors and see how they contribute to the definition of the position vector of P. Okay, so in this case, the P point over here should also have a position vector associated with it, right? So this angle, position vector will be defined as usual from starting from the origin and ending at the P point over here. So this will be the OP vector over here will be the position vector of P point, right? Okay, so where are exactly the unit vectors situated right now? So we will have to find three perpendicular unit vectors, right? So one of the unit vectors will be along this direction, right? This is self-explanatory. If you just compare the cases of Cartesian coordinate system, you will just get the hint and use it to find where these three unit vectors will be pointing at. So as for the variable r, we know that this is the distance of P point starting from the z-axis, right? So this is this line, the length of this line. So the AR vector, the unit vector over here, should be pointing towards the radial direction, all right? Okay, let's tidy up this picture a bit. All right, so the AR unit vector should be pointing directly outwards from the Z direction. Okay, so this will be the direction will be along the radial line over here. Just this was just the case in case of Cartesian systems, right? If you remember it right, if this was the x-axis, then the AX vector would point directly towards the AX direction, right? So the x-axis direction, right? So the AR vector over here will be directing along the radial line and towards the outward direction. This is important. So this will be pointing toward the outward direction from z-axis, all right? And then we will try to find the A5 vector over here. Now, let's say you took the radial line first and started from OX direction and started to move towards the anti-clockwise direction by an angle of phi. So if we looking straight down, we'll see that we are traversing in an anti-clockwise direction in a circular way, right? So this circle is always the direction of the tangent at any point drawn on the circle will always be perpendicular to the radius of the circle, right? We know that pretty well. So whenever we are traversing along a circle, we are always staying along its tangent, and we're by staying on traversing along the tangent, we are always staying perpendicular to the radius of the circle. Okay, so if this r is the radius of the circle, then this phi that we are traversing starting from the OX direction will always be along the direction of the tangent on any point on this circle, and at the same time the direction that we're traveling will always be perpendicular to the radius that we can draw over here. So the A5 vector will be along the phi coordinate. That means if we were to be on this position, the A5 vector will be along the tangent drawn on at this point over the circle. If we're to be on this point on the circle, the A5 vector will point towards the tangent on this point over here. And if this is the point we're talking about, this A5 vector will denote the direction of tangent and drawn at this point. Okay, This is a phi. All right, so this is AR, the direction, the outward direction along the radial line starting from z-axis. This will be the direction of AR. This is A phi, that is perpendicular to AR, because this is along the tangent line drawn at this point on the circle that we're traversing. And finally, these two are perpendicular, but uh, the z-axis is perpendicular to the circle over here, right? If we were to map this circle, this semicircle, sorry, the quarter circle in this 2D plane over here, the z-axis just adds an elevation to it. So this z-axis is just this circle elevated by a distance z. So the direction of AZ will be along the z-axis, will be parallel to the z-axis, all right? So extending the concept of polar coordinates to the 3D space, we're getting three orthogonal or perpendicular vector over here, as well as the Cartesian system. So these are the three coordinates. These are the three unit vectors that we'll be working with when we will be working with cylindrical coordinate system. Later in this course, you will find that in case of line charges, calculations will be a lot easier if we just add up the cylindrical coordinate system in place of the typical Cartesian coordinate system that we are familiar with. Okay, just as in the case of Cartesian coordinate system, we can also, in cylindrical coordinate system, we can also write the r, phi, and z coordinates as ar, a phi, and az if they are the components of a 3D vector a. All right. So the A vector over here is the OP vector shown over here. So the coordinates of P can be written as AR, A phi, and AZ. And just like in the previous case, we can write AR, AR, A phi smaller A phi, and AZ smaller AZ to denote the A vector in 3D space. In the green color over here, I've just shown you the direction of the unit vectors. All right. Hey, so as we just explained, the P point over here is the same in 3D space, but we're just using different sort of coordinate system to denote the position of it. So there must be a way to link up the cylindrical coordinates to the Cartesian coordinates, right? So we can, interchange the coordinate system if we have to. So if we were given the cylindrical coordinate systems, we should be able to convert them in the equivalent Cartesian notation or vice versa. To do so, let's just take the position of P in the Cartesian coordinate system as x, y, z, and according to the cylindrical coordinate system, let's say the positions are r, phi, and z. We have to be able to convert from Cartesian to cylindrical or cylindrical to Cartesian coordinate systems, all right? So let's do it. Let's say you were given the x, y, and z components, and you'll have to find the equivalent cylindrical coordinate notation of the same point. If you look over here, then if we name it like M and this point N, then the OMN is a right angle triangle as before, so we can write R as root over x squared and y squared, all right? Since this is a right angle triangle, we can just apply the Pythagorean theorem over here, and we also can get the value of phi. Let's say we are looking from the top straight down. So we'll be just looking at right angle triangle is sort of like this. This is x, this is y, this is r, and this is the angle phi. So phi from this triangle, we can write tan inverse y by x. Okay. And z is the same as before, sorry. Significance of z in case of Cartesian system is the same as cylindrical coordinate system. It just introduces an elevation to the point from the xy plane. It just pulls the point from and moves the point away perpendicularly from xy plane. So z in Cartesian system will also be the z in cylindrical system. Now let's say you are given the cylindrical coordinates and you will have to convert them into the Cartesian ones. Again, if you look at the right angle triangle here, over here, you can see the x is the component of r along the x-axis, all right, and y is the component of r along the y-axis, right? So we can write x as the cos component of r, the cos phi component of r, and y as the sine phi component of r, and the z will always be z. Okay, so these are the conversion rules.